We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will conclude our study of angular momentum by discussing several examples. We will start with examples in which there are no external torques acting on the system. In these cases, the angular momentum of the system, its magnitude, and its direction will be conserved. We will discuss the changes in angular velocities and kinetic energies that result from applying this conservation law. Finally, we will discuss an example in which the external torques acting on the system are not zero. Namely, we will discuss the gyroscope, in which the weight of a spinning top provides a torque that changes the angular momentum of the system. We will find that the top precesses in the horizontal plane about its pivot at a rate determined by the torque about the pivot and the angular momentum about the axis of the top. Last time we defined the angular momentum vector for a point particle about any axis and then used it to determine the expression for the angular momentum of a rigid rotating object. We determined that just as linear momentum is changed by the application of an external force, angular momentum is changed by the application of an external torque. Consequently, if the net external torque on a system about some axis is zero, then the angular momentum of the system about that axis is conserved. We will now do an example to illustrate these concepts. Here we see a particle sliding without friction on a horizontal surface. The particle is constrained to move in a circle by a string. We can write the angular momentum of the particle about the rotation axis as the product of its moment of inertia and its angular velocity. We now turn on a little motor at the center of the circle that slowly winds in some string so that the radius of the circle is reduced from r to r sub f. How will the angular velocity change, if at all? Well, the key here is to realize that there are no external torques acting about the rotation axis through the center of the circle. The torques generated by the normal force and the weight of the particle cancel, and the tension force generates no torque since its lever arm is zero. Therefore, the angular momentum of the particle about the axis will be conserved as the string is shortened. During this process, the moment of inertia of the particle will decrease. Therefore, its angular velocity must increase to keep the angular momentum constant. The final angular velocity increases by a factor of the ratio of the initial moment of inertia to the final moment of inertia. This analysis also explains why figure skaters, when they pull their arms and legs closer to their body, can spin faster, since they have reduced their moment of inertia about the axis of rotation. In the last example, we saw that the angular velocity of the particle increased as the string was shortened. How do we understand this result in terms of energy? Well, we know the kinetic energy of the particle at any time is just equal to 1/2 its mass times the square of its velocity. We can rewrite this expression in terms of the particle's angular momentum and moment of inertia about the rotation axis. Now, as the string was shortened, the particle's angular momentum remained constant, but its moment of inertia decreased. Therefore, its kinetic energy increased. In fact, the kinetic energy of the particle increases by a factor of the ratio of the initial moment of inertia to the final moment of inertia. Where did this kinetic energy come from? We know from the work kinetic energy theorem that positive work must have been done on the particle in order to increase its kinetic energy. This work was done by the tension force. While the particle is being pulled inward, there is a component of its motion which is parallel to the tension, and the dot product between force and displacement is non-zero. The total work done by the tension force must be equal to the change in the kinetic energy. To this point, the examples we have done to illustrate the conservation of angular momentum have only required consideration of the magnitude of the angular momentum. We will now consider an example in which we will need to explicitly deal with the vector nature of angular momentum. Here we see a student sitting on a stool that can rotate freely in the horizontal plane. The student holds onto an axle that supports a top that spins without friction in the counterclockwise direction. Initially, the student and the stool are at rest and the top is spinning in the horizontal plane. The student now flips the top over so that it is now upside down compared to its original orientation. What, if anything, happens to the student and the stool? In this case, we will choose to define the system to be comprised of the student, the stool, and the spinning top. The only connection this system has to the external world is the bearing about which the stool turns. Since the stool can rotate freely, there are no external torques acting on the system about this rotation axis. Therefore, the angular momentum of the system must be conserved. Initially, the angular momentum of the system is just equal to the angular momentum of the spinning top. Once the top is flipped over, though, the student and the stool must start to rotate so that the total angular momentum of the system will be conserved. Namely, the angular momentum of the student plus the stool plus the angular momentum of the top after the flip must be equal in both magnitude and direction to the angular momentum of the top before the flip. Therefore, the student and the stool end up rotating in the direction of the initial rotation of the top. To this point, we have focused on systems in which the total external torque was zero and angular momentum was conserved. We will now turn to a class of problems where there is an external torque. This external torque will result in a change of angular momentum, often referred to as precession. Here we see a disk spinning about its symmetry axis with an angular velocity omega. If the net external torque on this disk is zero, then its angular momentum will be conserved, which means that it will keep spinning with the same speed and remain in the same orientation. We now apply a torque to the spinning disk in a direction that is perpendicular to the axis of the disk. Since this torque is perpendicular to the symmetry axis of the disk, it will not change the angular momentum of the disk about this axis. However, the equation that relates the net external torque to the time rate of change of the angular momentum requires the total angular momentum of the system to change. How is this possible? Well, the answer comes from the equation itself. Namely, the direction in which the angular momentum changes is the same as the direction of the applied torque. Here we see the vectors representing the angular momentum of the disk about its axis and the external torque. The vector representing the change in the angular momentum must be parallel to the net external torque vector. When we add this vector to our original vector, we see the direction of the new angular momentum vector has changed, but its magnitude has not, since its magnitude must still be equal to the angular momentum of the spinning disk about its axis. The axis of the disk has simply turned a bit in the direction of the applied torque. As long as the torque is being applied, the disk will continue to turn. We call this motion of the axis of the disk precession, and we will treat it quantitatively on the next slide. The discussion on the last slide was qualitative. Its purpose was to make clear the mechanism that can produce the precession of a spinning disk. We will now take this analysis a step further by developing a quantitative description of this example. Here we see the vectors representing the angular momentum and the external torque applied to the spinning disk. This torque acts for a small time, dt, giving rise to a change in the angular momentum, dl, given by the product of the external torque and dt. During this time interval, the angular momentum vector rotates through an angle d phi. We can determine d phi using the small angle approximation. Namely, since dl is small compared to L, we can approximate dl as the product of L and d phi. If we now differentiate the expression for the angular momentum with respect to time, we find that the magnitude of the time rate of change of the angular momentum is equal to the product of the angular momentum of the disk and d phi dt. the precession rate of the disk. This precession rate is often denoted by the capital Greek letter omega. Now, we know that the time rate of change of the angular momentum of a system is always equal to the net external torque acting on the system. We can rewrite our expression for the precession rate as the ratio of the net external torque applied to the system to the angular momentum of the system. Now, omega has the same units as angular velocity, radians per second, and is exactly the angular velocity of the rotation of the axis of the disk as it is dragged around in a circle by the external torque. At this point, you probably have several questions. How could we actually apply such a torque that could cause this precession? What does this precession look like, really? Well, on the next slide, we will work out a concrete example that should make this all clear. Here we see a disk spinning about an axle through its symmetry axis. The axle is horizontal and is initially supported at both ends. In this configuration, the net external torque on the disk is 0, and the angular momentum of the disk is constant. We now remove the support on the left side, and the remaining support acts as a frictionless pivot. The weight of the disk will now provide an external torque about this pivot. This force acts through a lever arm equal to the horizontal distance from the pivot to the center of the disk. Using the right-hand rule, we see the direction of this torque is perpendicular to both the axle through the disk and the weight of the disk. In other words, this torque will always be perpendicular to the angular momentum of the spinning disk about its rotation axis, just as we discussed on the previous slide. Therefore, the disk will start to precess about the pivot. What will this precession look like? Just as we saw on the last slide, the angular momentum of the disk will turn in the same direction that the torque acts, as though it were being dragged around in a circle by the torque vector. This torque vector will always be parallel to the floor, so that the angular momentum vector will rotate in the horizontal plane. The rate of this precession is given by the ratio of the external torque produced by the weight of the disk to the angular momentum of the spinning disk. This rate is typically quite small. For example, if the mass of the disk is 1 kilogram, its radius is a half a meter, it is a half a meter from the pivot, and it spins with an angular velocity of 100 radians per second, we calculate the precession rate to be equal to 0.4 radians per second. In other words, it takes over 16 seconds to make one complete revolution. You may have noticed that our expression for omega blows up when the angular momentum of the disk approaches 0. Can we infer, then, that the precession rate goes to infinity as the angular momentum of the disk goes to 0? The answer is no, we can't. The problem is that the picture we have developed to derive this expression works well as long as the external torque is small compared to the angular momentum of the spinning object. Once this requirement is not met, the actual motion of the spinning disk becomes more complicated, and its calculation is beyond the scope of this course. We conclude with a brief discussion of the main points of this prelecture. First, we discuss some examples in which the angular momentum of a system was conserved, since there were no external torques acting on the system. We found that, for a particle executing circular motion with a slowly decreasing radius, that both the angular velocity and the kinetic energy of the particle increased by a factor equal to the ratio of its initial to its final moment of inertia about the center of rotation. Second, we discussed the gyroscope, in which the weight of a spinning top provides a torque that changes the angular momentum of the system. The magnitude of the angular momentum, determined by the spinning top, remains constant, but its direction changes in time. In particular, the torque causes the angular momentum to precess in the horizontal plane at a rate which is equal to the torque exerted by the weight of the top divided by the angular momentum of the spinning top.